So this project involves helping a robot lost in a maze find its way out. Rafael Espiricueta, and for my project I'm exploring a lost robot in a maze, helping it to get out, using discrete Markov processes to find an optimal policy, and using SLAM to localize the robot so it knows which policy to follow at which point in time. So here is the Bellman equation. It's the utility, the optimal utility at state S is the immediate reward for entering state S plus this discount factor, 0.99 is what I use, times the maximum over all possible actions A from S, the summation of states reachable by that action from S, S to S prime, over all possible reachable states S prime of the optimal utility of S prime. And this can be solved by iterating the very same function. So value iteration leads to the optimal solution U star. So by iterating value iteration here, iterating the Bellman equation essentially, you arrive at the optimal policy. So once you've converged from the sequence ut plus 1, so on, to U star, with the optimal utility that it converges to eventually, you end with the optimal policy P star of S, which is the argmax of the summation over all states reachable from S of the transition function from S to S star through action A of the optimal utility. Okay, this is an example of a sort of maze that Markov decision processes can solve. The policy that's the solution to it are the little arrows, basically. So at any given cell, you follow the arrows, it takes you straight to the goal. The red points are negative absorbing states, which are avoided. That's why you see all the arrows here moving away from those states. Anyway, this is the sort of world that I use to model the maze in a discrete way. This is more like the type of maze that I used for this problem. The corridors are quite a bit wider. It gives room for a continuous robot to move around better. So there's the goal up in the upper left corner, and the policy is basically to follow these arrows. And they all move away from the wall because you don't want the robot crashing into the wall. And if you follow these arrows, it'll take you to the goal without crashing into any walls along the way. Okay, here's a robot working its way through the maze. The red points that light up are the landmarks that are visible to the robot, and the cyan points are not visible. They're landmarks that aren't quite visible. And it's using SLAM to localize itself so it knows what policy to follow, what cell it's in, so that the discrete Markov process optimal policy can be followed. So it's making its way through. This is using a noise level of 0.02, which is 10% of the robot's stride. So it's a fairly noise-free environment. So it's being quite successful at working its way up to the goal, which is up in the upper left. Now for this animation, the robot is looking a little bit tipsy. The noise level has been set to double the robot's stride, so it's quite a lot of noise. But SLAM still manages to help to localize the robot enough that it can find its way through this maze still. It just does it in a rather drunken manner as it sort of meanders around. But it's still making its way through it, and it makes it all the way to the goal. In conclusion, it worked quite well using SLAM to localize the robot so it knew what cell it was in to follow the policy iteration that was created by the discrete Markov decision process. So I used value iteration, it found the policy, and SLAM allowed the robot to know where it was well enough to follow that policy. And even with huge noise, even 3 times the robot's stride, it was able to find its way through the maze.